Stars go through an amazing and intricate process called life and death that spans billions of years. The life cycle of a star is examined in this documentary, starting from its birth in a nebula and ending with its spectacular explosion as a red giant or supergiant. Although the Crab Nebula is a frequently used illustration of a star dying, we will explore other, lesser-known examples, such as the Bubble Nebula. Nebulae, which are enormous clouds of gas and dust in space, are where stars are born. These nebulae are the star nurseries. Examples are the well-known Orion Nebula and the charming Bubble Nebula. Pockets of gas and dust within these nebulae start to collapse due to gravity. The temperature and pressure inside these pockets rise as they contract, eventually causing nuclear fusion to ignite within their cores. This is the beginning of a new star. A star enters what is referred to as the main sequence phase, after it has lit up its nuclear furnace. The star's core converts hydrogen to helium during this period, which can last billions of years. This process releases energy that makes the star glow and creates the external pressure required to keep the star stable by balancing the forces of gravity. A good example of this stage is the main sequence phase that our Sun is currently in. The star's core shrinks and heats up as it runs out of hydrogen fuel, which causes the star's outer layers to expand. Due to this expansion, the star swells dramatically, becoming a red giant, or in the case of stars with higher masses, a supergiant. The core's fusion of heavier elements is what defines this phase. An example of a well-known red giant star is the well-known star Aldebaran in the Taurus constellation. The supernova is the most spectacular phase of a massive star's life cycle. A massive star collapses when its nuclear fuel runs out, and the core is unable to support the weight of the star. The supernova, a devastating explosion, is caused by this collapse. Supernovae are some of the universe's most intense events. For a brief while, they can outshine entire galaxies. SN 1054 remnants in the Bubble Nebula are one prominent example. Astronomers in antiquity witnessed this amazing explosion, which has since sparked extensive research. A striking reminder of the immense forces at work in the universe is provided by the Bubble Nebula, whose complex structure was created from material that the supernova ejected. A star's life cycle, which begins in a nebula, ends dramatically in a supernova, and eventually dies as a red giant or supergiant, is evidence of the universe's dynamic and ever-changing nature. The study of various nebulae such as the Bubble Nebula, which provide insightful information about these processes, enriches our knowledge of the cosmic life cycle of stars. When a star dies, especially in a supernova, it is not only the end but also the beginning, because the elements created in these explosions are dispersed throughout space and become seeds for new stars and planet formation in the future. The Bubble Nebula, also known as NGC 7635, is an emission nebula located 8,000 light-years away from Earth in the direction of the Cassiopeia constellation. Famous astronomer William Herschel made the initial discovery of the nebula in 1787, and scientists have since taken pictures of it with Hubble. However, the vast nebula was only partially visible in those earlier views. 10 light-years across, the bright star visible to the left of the centre sculpts the Bubble Nebula. This is a mind-boggling rate of expansion of about 62,000 miles per hour. Researchers state that, although the sphere already measures around 10 light-years in diameter, it is still growing, owing to the constant pressure of the stellar wind, currently at more than 100,000 kilometers per hour. SAO 2575, a star that can have a mass up to 20 times that of the Sun, and is the source of the stellar wind that is forming a bubble in space out of the interstellar dust around it, is at the center of the nebula. In addition, cometary knots, of which there is one visible directly to the star's right, are found all around the star. These crescent-shaped dust globules have a mass equal to that of Earth and a size greater than that of the solar system. Amidst the Bubble Nebula's breathtaking beauty lies a scientific enigma. Astronomers are baffled by the fact that the bubble's parent star, SAO 2575, is not at its center. Astronomers are still discussing why this is the case and how the perfectly round bubble is created nonetheless. Since its estimated explosion in 1671, Cassiopeia A, also known as Cass A, a relatively recent supernova remnant located about 11,000 light-years away, has captivated astronomers. It is unique in the universe because of its brilliant shell of high-energy particles. Cass A, a 10-light-year diameter remnant that is among the most studied in the X-ray spectrum, is essential to our knowledge of neutron star formation and supernova aftermaths. A star whose demise was observed 325 years ago has been found to have an echo. As light waves, not sound waves, are released, the reverberation suggests that the stellar remnant released a powerful explosion about half a century ago. The dead star in question is Cassiopeia A, whose supernova explosion Tycho Brahe observed in 1572. Astronomers estimate that a dense neutron star is all that remains of the original star, which is located 10,000 light-years away. Until the recent discovery of a light echo in infrared images captured by NASA's Spitzer Space Telescope, it was believed that this neutron star remnant was peacefully resting. "We had thought the stellar remains inside Cassiopeia were just fading away," said Oliver Krauss of the University of Arizona. "Spitzer came along and showed us this exploded star, one of the most intensively studied objects in the sky, is still undergoing death throes before heading to its final grave." A Spitzer test image revealing glowing dust features surrounding the dead star served as the first piece of evidence for this post-mortem activity. Subsequent examinations revealed that the entwined characteristics had expanded outward, seemingly at the speed of light. The truth was that, rather than the dust moving, the light waves that were stirring it up had expanded. This is the first time a light echo around a long-dead star has been seen, and it is also the largest one ever recorded. The researchers deduced that there was a bang on the neutron star in 1953 by following the light waves from the echo backwards. Given its recent activity, Cassiopeia A might be a magnetar, an uncommon kind of neutron star. Massive amounts of high-energy gamma rays are released when the surfaces of these bizarre objects rupture and tremble. George Reiki of the University of Arizona stated that magnets are extremely uncommon and challenging to study, particularly if they are not connected to their original location. Cassiopeia A's post-death life may be better understood if Spitzer observations are conducted. If we have indeed uncovered one, then it will be just about the only one for which we know what kind of star it came from and when. Approximately 800 light-years away in the southern sky, the Vela supernova remnant bears witness to a cosmic event that transpired 11 to 12,000 years ago. Its intricate structure, observable at radio, optical and X-ray wavelengths, provides an abundance of opportunities to investigate interactions with the interstellar medium. Our knowledge of these cosmic phenomena is further enhanced by the Vela remnant, which is recognized as the Vela pulsar and spans roughly 100 light-years. A stunning new perspective on the Vela constellation depicts the stunning fallout from a massive star explosion. A supernova, which is a bright, fiery explosion that occurs when a star reaches the end of its life, is produced. A new image obtained by the European Southern Observatory, ESO, shows the expanding material ejected from such an explosion and the resulting glowing interstellar material left behind. The supernova remnant is the remnant of a starburst that took place roughly 11,000 years ago and is situated in the constellation Vela. Beautifully illuminated clouds of interstellar dust and gas, dotted with sparkling stars, can be seen in a small but intricate portion of the remnant, visible in the ESO view. The star would have shone so brightly during this violent event that it could be seen during the day, a statement from ESO officials stated. Supernovas emit more energy in a brief amount of time than our Sun will in its entire lifetime, making them capable of momentarily outshining an entire galaxy. Because of how long it takes for light from far-off space to reach Earth, even though the supernova occurred thousands of years ago, its light was only recently detected. The new photo of the Vela supernova remnant was taken with the Very Large Telescope, VLT, of the European Southern Observatory, ESO. It shows the bright blue stars and bright pink gaseous filaments in the foreground in a detailed manner. With a 286 million pixel Omega cam featuring filters ranging from ultraviolet to near-infrared, the VLT is housed at ESO's Paranal Observatory in Chile's Atacama Desert. In the statement, ESO officials stated that Omega cam is capable of capturing images through multiple filters, each of which allows the telescope to observe the light emitted in a unique color. To capture this image, 4 filters have been used, represented here by a combination of magenta, blue, green, and red. About 7,000 light-years away, SN 1006 was discovered more than a millennium ago. This remnant is easily recognized by its bright circular rim, which spans roughly 60 light-years. SN 1006 has been a focus for scientists studying supernova expansion and interaction with surrounding space because it is historically significant and essential for cosmic ray research. About 8,000 light-years away is Tycho's supernova remnant, which Tycho Brahe first observed in 1572. It is a crucial object for comprehending Type Ia supernovae because of its nearly circular shape and brightness in radio and X-ray wavelengths. In order to shed light on the nature of the explosion and the resulting neutron star, research here has focused on the distribution of elements within the remnant. According to a new study, supernova remnant SN 1006 may be a cosmic ray accelerator. A recently developed X-ray telescope demonstrated how shock waves from star explosions align strong magnetic fields that can accelerate fragments of atoms nearly to the speed of light. The discovery was made at the remnant known as SN 1006, which is a supernova explosion. NASA and the Imaging X-ray Polarimetry Explorer, IXPE, of the Italian Space Agency examined it closely. The high-energy X-rays from the supernova were measured by the Space Telescope, which was launched in December 2021. What's left of a Type 1 supernova is called a remnant. This type emits explosions when an old star core or 2 white dwarfs collide, or when a white dwarf gains excessive mass from a companion star. The International Astronomical Union currently refers to the constellation Lupus, the Wolf, as the location of the explosion in 1006 that gave rise to SN 1006. It was observed all the way to the Arab world and in areas that are now a part of Europe, Asia, and Japan. Additionally, it is thought that the supernova was the brightest in recorded history. The supernova, which was 6,500 light-years away, was so bright that it could be seen for 3 years in the night sky with no assistance, according to prehistoric records. IXP demonstrated that magnetic fields oriented in a particular way within the expanding supernova's remnant of gas and dust cause the X-ray light to be polarized or the X-ray photons to oscillate or vibrate in a preferred direction. Lead researcher Ping Zhou of Nanjing University in Jiangsu, China said, "Now we can see that SN 1006 magnetic fields are turbulent, but also present an organized direction." Since at least some cosmic rays are thought to have originated from supernova remnants, it is imperative to comprehend the arrangement and direction of magnetic fields within these remnants. These rays are made up of charged particles like protons, electrons, and some ions that were propelled by strong magnetic fields in the supernova to speeds that were almost equal to light. Although the precise source of cosmic rays has not been determined, many scientists believe that they originate from supernovas. The NASA statement also mentioned that previous observations of supernova remnants like SN 1006 indicate that they could serve as particle accelerators and that cosmic rays could originate from the nearby nebula or gas cloud. The results of IXP now indicate that the magnetic fields inside the supernova are oriented in a way that is opposite to the point where the explosion of the supernova occurred. 2 other supernova remnants studied by IXP show evidence for radially outward-oriented magnetic fields, Cassiopeia A, whose light probably reached Earth in the 1660s, and a supernova remnant observed by Danish astronomer Tycho Brahe in 1572. In contrast to the other 2 supernovas taken into consideration in the study, the X-rays from SN 1006 are noticeably more polarized, offering far more convincing evidence for the magnetic field phenomenon. Our spectral polarimetric analysis yielded polarization properties that compare remarkably well with results from other techniques and X-ray observatories, said Yijing Yang, a co-author of the study from the University of Hong Kong. The magnetic fields are found to align with the direction of the supernova shockwave as it moves through the gas and dust surrounding the supernova. After the shockwave has carried charged particles up and caught them in the magnetic field lines, they accelerate. The heliospheric bubble, which surrounds the solar system and is blasted by the solar wind, or charged particles that radiate from our sun, is breached by those cosmic rays as they continue their journey through space. When the rays finally reach Earth, they collide with molecules in the atmosphere on the final part of their journey. Every collision breaks the molecule into an air shower of short-lived muons, or daughter particles, decay products left over after a molecule breaks apart. Cosmic ray detectors are able to record the echoes of long-dead stars as the muons rapidly decay in a burst of light. Finally, the Vela Nebula, also known as the Cygnus Loop, is a massive supernova remnant located in the constellation Cygnus, approximately 1,500 light-years away from Earth. This amazing sight was the result of an explosion that happened 8,000 years ago. The Cygnus Loop is a 45 light-year wide region that is well known for its exquisite, complex filaments and a mixture of red, blue and purple colours. An excellent resource for learning about the life cycle of stars and how they interact with the interstellar medium is this nebula. Because of their distinctive qualities and the substantial research they have sparked, each of these supernova remnants has made a substantial contribution to our understanding of the universe. In addition to shedding light on what happens after a star dies, their research provides an understanding of the larger cosmic story of stellar evolution and the formation of our galaxy. The astronomical marvel Kepler's supernova, discovered in 1604 and situated approximately 20,000 light-years away in the constellation Ophiuchus, is another one. Its spherical shock front provides important insights into Type I supernovae, being bright in radio and X-ray emissions. The composition of the material ejected and its dynamic expansion have been the main focus of research on Kepler's supernova. After examining the last massive star explosion in our galaxy that was visible to the unaided eye, scientists have concluded that a compact white dwarf, with more heavy elements than the Sun, caused the supernova. In 1604, the supernova appeared out of nowhere in the night sky. At its brightest, it outshone all other stars and planets. The German astronomer Johannes Kepler believed he was witnessing the birth of a new star. After many centuries, researchers discovered that Kepler's observation was, in fact, an exploding star, which they dubbed Kepler's supernova. The recent cosmic autopsy, made possible by X-ray observations from the Japan-led Suzaku satellite, may help scientists better understand the phenomenon known as Type Ia supernovae. An official statement from NASA quoted Carl Badenes, an assistant professor of physics and astronomy at the University of Pittsburgh, as saying, "Kepler's supernova is one of the most recent Type Ia explosions known in our galaxy, so it represents an essential link to improving our knowledge of these events." It is believed that Type Ia supernovae arise from binary systems in which at least one star is a white dwarf or a tiny, extremely dense core of a star that has stopped going through nuclear fusion reactions. The white dwarf may receive gas transferred from one of the normal stars in the pair, or if both stars in the system are white dwarfs, their orbits may contract until they merge. Under both scenarios, an internal runaway nuclear reaction culminates in a brilliant supernova when the white dwarf or white dwarf conglomerate becomes overly massive, about 1.4 times the mass of the Sun. Using 2009 and 2011 Suzaku satellite X-ray imaging spectrometer observations, Badenes et al. Probed the chemical signatures in the shell of hot, rapidly expanding gas left behind by Kepler's supernova to gain a better understanding of the star's composition prior to its explosion. A bright emission line from iron was visible in the X-ray spectrum, along with weak emissions from highly ionized nickel, manganese, and chromium. According to the ratios of these trace elements in the supernova remnant, the original white dwarf most likely contained 3 times as much metal as the Sun does, the researchers said. The estimated distance of Kepler's supernova remnant is 23,000 light-years. It is much closer to the central region of the Milky Way, which is densely populated and likely saw more rapid and efficient star formation than our solar system, leaving interstellar gas enriched with higher proportions of metals. This explains why material with a higher metal fraction was used to form Kepler's supernova. The nature of the binary system that caused the supernova was not determined by the study, but the researchers estimate that the white dwarf that burst was no older than 1 billion years, or about a quarter of the age of the Sun. Sang-Wook Park, an assistant professor of physics at the University of Texas at Arlington, stated in a statement that theories indicate that the star's age and metal content affect the peak luminosity of type Ia supernovae. Younger stars likely produce brighter explosions than older ones, which is why understanding the spread of ages among type Ia supernovae is so important. Park continued, "We can improve cosmological models that depend on those measurements and fine-tune our knowledge of the universe beyond our galaxy by better understanding type Ia supernovae." In 2011, American and Australian astronomers were awarded the Nobel Prize in Physics for their finding that the universe is expanding faster than before. This finding was based on measurements of type Ia supernovae, which gave rise to the theory of dark energy. The mystery of black holes. Black holes are among the most intriguing and mysterious objects in the universe, and they have long piqued interest in astronomers and the general public. These are areas of space-time where gravity is so intense that nothing can evade it, not even light. In addition to research by eminent astronomers, this essay explores the formation of black holes from supernovae, their various types, stellar, supermassive, and intermediate, their physical characteristics, known discoveries, and the theories surrounding them. Large stars' remnants frequently form black holes. A star explodes in a supernova when its life cycle ends, and its mass exceeds roughly 20 times that of our Sun. As a result of the star running out of nuclear fuel and collapsing due to gravity, this explosion occurs. As temperatures rise and the core contracts, a catastrophic explosion occurs. The collapse of the core remnant results in the formation of a black hole if its mass exceeds approximately 3 solar masses. As mentioned above, massive stars collapse due to gravity to form stellar black holes. Their masses usually vary from a few tens to several hundred solar masses. Cygnus X1, one of the most well-known stellar black holes, was found in 1964. With a mass of roughly 14.8 times that of the Sun, it was one of the first objects to be identified as a black hole by the general public. Supermassive black holes, which are millions to billions of times more massive than the Sun, are at the other extreme. These enormous objects are located at the center of most massive galaxies, if not all of them. Sagittarius A, the supermassive black hole at the center of our Milky Way galaxy, is roughly 4.3 million times as massive as the Sun. Another noteworthy example is M87, the supermassive black hole in the galaxy M87, which made headlines in 2019 when the Event Horizon Telescope captured its first ever direct visual image of a black hole. As their name implies, intermediate black holes are mid-sized black holes with masses between hundreds and thousands of solar masses. Compared to their stellar and supermassive counterparts, they are less well understood and more difficult to detect. Their presence aids in the understanding of potential growth routes leading to supermassive black holes by astronomers. The boundary that nothing can escape from, known as the event horizon, is what distinguishes black holes. Even though they aren't visible in the conventional sense, their existence can be assumed from the way they affect nearby materials. An accretion disk, for instance, could be formed if they were to accrete material from companion stars or the interstellar medium. When this material heats up, it emits X-rays that can be detected by instruments. The accretion disks surrounding black holes emit a great deal of light, which frequently appears blue due to Doppler shifting and X-ray emissions, despite the fact that black holes themselves are invisible. The event horizon creates a spherical area in space, while the black hole itself is a point of singularity with no volume. Light bending around the event horizon produces a bright ring surrounding a dark central region, which is how the black hole's shadow is depicted in the M87 image. The existence of black holes was later confirmed by a number of observations and discoveries in Albert Einstein's general theory of relativity. Hawking radiation is the term used to describe Stephen Hawking's research on the possibility that black holes could release radiation as a result of quantum effects close to the event horizon. Roger Penrose and Carl Schwarzschild, among others, have made substantial contributions to the theory of black holes. The Schwarzschild radius, a measurement of the event horizon's size, was developed as a result of Schwarzschild's solution to Einstein's field equations. Penrose proposed the idea of a singularity, or the point at which the standard laws of physics collapse, at the center of a black hole. For their work on the supermassive black hole at the center of our galaxy, which provided compelling evidence of its existence through stellar motion studies, Reinhard Genzel and Andrea Ghez were granted the 2020 Nobel Prize in Physics. The mass of a black hole directly relates to the size of its event horizon. For instance, a solar mass black hole's Schwarzschild radius, or the event horizon's radius, is roughly 3 kilometers. On the other hand, M87's massive size is reflected in its event horizon, which has a diameter of roughly 24 billion kilometers. Astrophysics' most fascinating topic is still black holes. Their research raises important questions about physics and offers vital new insights into the universe's and galaxies' evolution. Our understanding of these cosmic occurrences keeps growing as new theories and improved observational methods provide a window into the universe's most extreme circumstances. Among them is GRS 1915, a black hole in the constellation Aquila that is roughly 36,000 light-years distant. With an estimated mass of 14 solar masses, it is noteworthy for being one of the most massive stellar black holes. Relativistic jet emissions from GRS 1915 are especially well known. They span thousands of light-years. These jets serve as evidence of the tremendous force black holes have when it comes to propelling particles almost as fast as light. As a component of a binary system, the black hole absorbs material from its companion star. The high-energy emissions and amazing jet formations seen are caused by this accretion process. GRS 1915 has been used by scientists to learn more about the peculiarities of jet formation and the harsh environments that surround black holes. It functions as a laboratory for research into the physics of jet production and accretion, two important processes that are relevant to a variety of astrophysical phenomena, in addition to black holes. Located in the constellation Cygnus and roughly 8,000 light-years away, V404 Cygni is another fascinating black hole. It was initially recognized as a black hole in 1989 and is well known for its unpredictable and wildly fluctuating behavior. V404 Cygni is a stellar black hole because its mass is thought to be roughly 9 times that of the Sun. The black hole and its low-mass star companion are components of a binary system. Episodic outbursts, in which the black hole's accretion rate abruptly increases and causes a sharp increase in brightness, are the system's defining feature. These explosions shed important light on the dynamics of accretion processes surrounding black holes. High-velocity material ejections from V404 Cygni can be seen during these episodes at a range of wavelengths, including radio and X-rays. Astronomers can learn more about the interactions between black holes and their surroundings, especially in binary systems, by studying V404 Cygni. The 2018 discovery of the black hole, MAXI J1820, is situated in the constellation Leo, roughly 10,000 light-years away. Due to its high luminosity, it attracted attention very quickly, and during its outburst period it became one of the brightest X-ray sources in the sky. The mass of the stellar mass black hole MAXI J1820 is estimated to be around 8 solar masses. It is accumulating material from a companion star as a component of a binary system. The high-energy emissions from this system have been observed by numerous space telescopes, yielding a wealth of data. Astronomers have been able to examine the behavior of matter under intense gravitational forces as well as the deepest areas of the accretion disk, thanks to the system's brightness fluctuations. We have also gained further insight into the behavior of matter under a black hole's powerful gravitational pull, thanks to observations of Maxi J1820. The physics of accretion disks and the consequences of relativity under these extreme circumstances have been clarified by these observations. 2011 saw the discovery of Swift J11644, a peculiar and intriguing black hole in the Draco constellation that is roughly 3.9 billion light-years away. It was found because of a sudden and intense energy burst that was first believed to be a gamma-ray burst, but was later determined to be a tidal disruption event, which is the result of a star being torn apart by a black hole's strong gravitational pull. This occurrence offered a unique chance to witness the instantaneous aftermath of a star's disintegration and the consequent accumulation of its constituents into a black hole. With an estimated mass several million times that of the Sun, Swift J11644 belongs to the class of supermassive black holes. Understanding the dynamics of tidal disruption events and the behavior of disrupted material as it falls into a black hole has been made possible thanks in large part to Swift J11644 observations. This incident also provided information about the nature of jet formation because the disruption resulted in the formation of a strong relativistic jet that was visible at a variety of wavelengths, including radio and X-rays. One of the largest known black holes is the central black hole of NGC 4889, which is located in the Coma cluster, a massive elliptical galaxy about 308 million light-years away. An estimate of its mass places it at around 21 billion times that of the Sun. The black hole in NGC 4889 offers an important window into the properties and dynamics of supermassive black holes in massive galaxies. This black hole's immense size provides information about the mechanisms governing the development of supermassive black holes and their impact on the host galaxies. The study of NGC 4889 and its central black hole has advanced our knowledge of the formation of galaxies and the influence that supermassive black holes have on their surroundings. The study of such massive black holes sheds light on the intricate relationship between black holes and galaxy formation, as well as casting doubt on current theories of black hole growth. The last black hole of note is located in NGC 1277, a compact lenticular galaxy located approximately 220 million light-years away in the Perseus cluster. It is notable for its disproportionate size in comparison to its host galaxy, with a mass estimated to be roughly 17 billion times that of the Sun. The black hole is exceptionally massive for a galaxy the size of NGC 1277. The traditional understanding of the relationship between black holes and their host galaxies has come under scrutiny in light of this discovery. The black hole in NGC 1277 contradicts the theory that black hole growth is always in step with host galaxy growth. Investigating this system offers important new understandings of the variety of black hole galaxy interactions and potential black hole growth routes. Furthermore, it raises the possibility that the universe contains more of these disproportionately massive black holes, which calls into question accepted beliefs about black holes and galaxy coevolution. Although black holes cannot be seen, astronomers can identify them by observing the effects of the immense gravity these tiny spheres of space create on other objects. The region immediately surrounding a black hole can release intense radiation, as incoming material is superheated and accelerated to a significant fraction of light speed. This should be a very messy and complex environment, but no matter how massive the black hole is, the stuff flowing onto different black holes looks the same, said Barry McKernan, an astrophysicist at the City University of New York's Borough of Manhattan Community College and the American Museum of Natural History in New York. Supermassive black holes are found at the centers of 245 active galactic nuclei, which McKernan and associates examined data from. These black holes have the ability to release intense radiation beams with the brightness of billions of stars, and they feed on gas that falls into them. The mass of the black holes under study ranged from 1 million to 100 million times that of the Sun. In particular, the researchers measured the infrared and X-ray light surrounding these black holes in order to test a theory regarding the connection between these two extreme radiation types. They were aware that infrared light should originate from warm material farther away from the black hole, while X-rays should originate from hot material near the black hole. By using this pattern, the researchers were able to determine whether the matter surrounding the black hole was being observed edge-on, which shows only the side of the donut-shaped structure, or face-on, which looks directly down onto the black hole ringed by X-rays and infrared light. Additionally, a portion of the donut that has been freed by X-ray bombardment should contribute some infrared light. McKernan and his colleagues indirectly determined how the material might be distributed around a black hole by comparing the ratio of X-rays to infrared light coming from around the black hole. The researchers discovered that 90% of the active galactic nuclei that were observable face-on had nearly the same ratio of X-ray to infrared light after dividing the data into those observed edge-on and those observed face-on. The material surrounding the black hole assumed the shape of a donut with a black hole in the center, regardless of how heavy it was. There are many different types of black holes, ranging from tiny stellar mass bodies to the massive monsters that live at the center of galaxies. Supermassive black holes, which have masses millions to billions of times that of the Sun, are believed to be present in the cores of nearly all galaxies. The largest known black holes were found by scientists in 2 nearby galaxies in 2011. Located approximately 320 million light-years away, NGC 3842, the brightest galaxy in the Leo cluster, is one of these galaxies. Its central black hole has a mass of 9.7 billion solar masses. The black hole in the other galaxy, NGC 4889, which is the brightest galaxy in the Coma cluster and is located more than 335 million light-years away, is at least as massive. These black holes' gravitational range, or event horizon, is roughly 5 times the separation between the Sun and Pluto. In contrast, the black hole at the center of the Milky Way galaxy, whose event horizon is 1/5 the orbit of Mercury, is only 2,500 times as massive as these black holes, the smallest known black hole. The world's smallest known black hole could be found in the binary star system IGR J17091. By examining the heartbeat-like pattern of X-rays that are assumed to be released from a disk of accreting matter surrounding the black hole, scientists were able to find it. It's possible that the smallest black hole ever found is less than 3 times as massive as the Sun. This would place this small monster, officially designated IGR J17091, in close proximity to the theoretical minimum required for the stability of a black hole. Despite its small size, this black hole appears to be extremely powerful, with winds of up to 20 million mph, 32 million kph, which is nearly 10 times faster than any other recorded from a stellar mass black hole. Anything that is unlucky enough to drift too close to a black hole is devoured, including other black holes. Researchers have discovered that a larger black hole in another galaxy is consuming the enormous black hole at the center of the first galaxy. It's the first discovery of its kind. Minor mergers between galaxies and smaller companions had long eluded researchers, but astronomers had seen the final stages of the merging of galaxies of equal mass, or so-called major mergers. Researchers used NASA's Chandra X-ray Observatory to find 2 black holes at the center of a galaxy known as NGC 3393. The 2 black holes are only 490 light-years apart, with one having a mass of about 30 million times that of the Sun, and the other at least 1 million times that. Although black holes are known to draw matter in, scientists have discovered that they can also expel matter. The black hole known as H1743, which is roughly 28,000 light-years from Earth and contains 5 to 10 times the mass of the Sun, has been observed to spit some matter back out of a companion star in the form of massive bullets of gas, travelling at almost a quarter the speed of light. Officially known as ULAS J1342, the oldest black hole ever discovered was formed approximately 690 million years after the Big Bang that created our universe. According to scientists, the Big Bang happened roughly 13.7 billion years ago. Astronomers are actually faced with some challenges because of this black hole's ancient age. It seems that the mass of this luminous mystery is 1 billion times that of the Sun. It is hard to understand how black holes got to be so massive so soon after the Big Bang. At the center of quasars, the most bright, strong and energetic objects in the universe, are black holes, whose gravitational pull is so great that even light cannot escape from them. Huge amounts of energy can be released by supermassive black holes at the centers of galaxies as they suck in surrounding gas and dust. J043947 is the brightest quasar found to date. It is located approximately 12.8 billion light-years from Earth. Uncontrolled black holes. Black holes can be ejected from the scene of a galaxy collision and set free to travel across space. SDSS J0927, the first known rogue black hole, may have a mass of 600 million times that of the Sun and accelerate through space at an astounding 5.9 million mph. There could be hundreds of stray black holes in the Milky Way. For a very long time, scientists believed that there are three sizes of black holes: small, medium, and large. While supermassive black holes with millions to billions of solar masses are believed to be lurking at the center of almost every galaxy, relatively small black holes with the mass of a few suns are more common. For example, it is believed that there is one more massive than 4 million suns hiding in the center of the Milky Way. However, until 2009, astronomers had been unable to identify middleweight black holes. At that time, researchers found HLX-1, Hyperluminous X-ray Source 1, one of the first intermediate mass black holes, roughly 290 million light-years from Earth. The size of the enigmatic object seems to be approximately 20,000 solar masses. Gaining more knowledge about medium-sized black holes can help us understand how these monsters and the surrounding galaxies evolved. It is believed that medium-sized black holes are the building blocks of supermassive black holes. Pulsars and neutron stars. Some of the universe's most extreme and fascinating objects are pulsars and neutron stars. These dense objects, which are the remains of massive stars that experienced a supernova explosion, are only a few tens of kilometers in diameter but contain a mass larger than the Sun. The nature of neutron stars and pulsars, their physical properties, known discoveries, theoretical foundations, and the important contributions made by astronomers to our understanding of these celestial phenomena are all covered in this essay. The densest objects in the universe are neutron stars. The collapsed cores of massive stars that remain after a supernova explosion are known as neutron stars. 1 teaspoon of neutron star material weighs roughly 1 billion tons, demonstrating their extreme density. Neutrons, which are particles produced when the atomic structure collapses under extreme gravitational pressure, make up the majority of these stars. A neutron star's radius is normally between 10 and 20 kilometers, but its mass can be as much as twice that of the Sun. Some of the universe's strongest surface gravitational fields are produced by their enormous gravity. Additionally, because of the star's strong gravity, light bends around it in a phenomenon called gravitational lensing, which occasionally lets observers see part of the star's backside. The magnetic fields of neutron stars are millions or even billions of times stronger than those of Earth. Numerous phenomena seen in neutron stars, including the emission of electromagnetic radiation seen in pulsars, are caused by these magnetic fields. The universe's lighthouses, pulsars. A particular kind of neutron star known as a pulsar radiates electromagnetic beams from its magnetic poles. These beams sweep across the sky as the star rotates. If one of these beams happens to cross the Earth's line of sight, it can be observed as a radiation pulse, hence the name pulsar. The regularity of these pulses can be extremely precise, frequently matching the stability of atomic clocks. In 1967, Jocelyn Bell Burnell and Anthony Hewish made the initial discovery of pulsars. The first pulsar, designated PSR B1919, was thought to be a signal from an advanced extraterrestrial civilization because of its clock-like regularity in emitting radio waves. Since then, pulsars have been discovered in a variety of settings, such as the centers of globular clusters, binary systems, and the remains of supernovae. The existence of planets orbiting some pulsars casts doubt on our knowledge of planet formation and survival. Although neutron stars and pulsars are invisible to the unaided eye, they can be seen with telescopes that use gamma, X, and radio wavelengths in the electromagnetic spectrum. In these observations, Their colour frequently varies according to the region of the spectrum being examined. For example, because of their extremely high surface temperatures, neutron stars can appear as hot, blue-white objects in X-rays. Because of the strong gravitational pull that exists on a neutron star, its shape is nearly spherical. On the other hand, strong magnetic fields can deform objects, and in the case of pulsars, these fields are what produce the radiation beams. Only 2 years after the discovery of the neutron in 1934, Walter Baade and Fritz Zwicky made the first prediction of neutron stars. Nonetheless, the existence of neutron stars was verified by the discovery of pulsars. Situated at the centre of the Crab Nebula, the Crab Pulsar is one of the most well-known pulsars. This pulsar is quite young, having formed during a supernova explosion that was witnessed on Earth in 1054. Because of its relative youth and the volume of available data, the Crab Pulsar is a vital resource for research on the physics of neutron stars and pulsars. Over the years, many astronomers and physicists have studied neutron stars and pulsars. In addition to Bell Burnell and Hewish, Russell Hulse, who made the first binary pulsar discovery in 1974, and Joseph Taylor are also noteworthy contributors. The pulsar's orbit was found to decay over time in a way that was consistent with Einstein's theory of general relativity, which was a significant discovery in supporting the theory. Although their sizes vary, neutron stars typically have a diameter of 20 kilometers. Because of their extreme density, 3 billion tons of neutron star material would weigh the same as a matchbox on Earth. The rotational speed of neutron stars is one of their most fascinating characteristics. PSR J11748, the fastest pulsar currently known to science, rotates at an astounding 716 times per second. Pulsars and neutron stars offer a singular window into the physics of the extreme. They put our knowledge of matter to the ultimate test in extreme magnetic fields and pressures. These objects provide insights not only into the life cycles of stars but also into basic physics, such as the nature of gravity and the behavior of matter at nuclear densities. Our understanding of these extraordinary objects keeps expanding as new theories and improved observational methods are developed, providing more insight into the most extreme conditions found in the universe. J0348 is the neutron star. The neutron star, known as PSR J0348, is notable for both its extremely high mass and the accuracy with which its characteristics have been determined. The binary system also includes a white dwarf star. This neutron star is one of the most massive known neutron stars due to its mass, which is approximately twice that of the Sun. This measurement of mass is important because it offers a rigorous test for the physics of dense matter. PSR J0348, extreme density and gravitational pull have been used to test theories of gravity and dense matter because they have a significant impact on the orbit of its companion white dwarf. With a rotation period of slightly over 39 milliseconds, PSR J0348, a neutron star in the Taurus constellation, rotates rather slowly for a star its distance. It is located approximately 7,000 light-years away. Due to the system's extensive observation at radio wavelengths, astronomers are able to measure its properties with a remarkable degree of precision. Understanding the equation of the state of neutron star matter, a fundamental question in physics related to matter's behavior at nuclear densities, will be impacted by the investigation of PSR J0348. RxJ 1856.5 is the neutron star. Situated in the Corona Australis constellation, RxJ 1856 is a lone neutron star that is roughly 400 light-years away. It is the focus of extensive research because it is one of the nearest known neutron stars to Earth. Estimated to be only 500,000 years old, this neutron star is travelling through space quickly, most likely as a result of a supernova kick. RxJ 1856 is especially intriguing because of its thermal emission, which enables direct study of the star's surface by astronomers. Its temperature is surprisingly uniform across its surface, as determined by valuable data obtained from observations made at optical and X-ray wavelengths. This homogeneity puts to the test current models of heat distribution and atmospheres of neutron stars. Its radius of roughly 14 km makes it one of the few neutron stars for which direct measurements of radius have been made. greatly advancing our knowledge of the composition and size of neutron stars. The Pulsar B1937 Pulsar. When Pulsar B1937 was found in 1982, it was the first pulsar detected in milliseconds. It is one of the fastest spinning pulsars known, with a rotation period of only 1.6 milliseconds. It is situated in the constellation Vulpecula, roughly 10,000 light-years away. The star has spun up, or recycled, by accreting material from a companion star, which is the cause of its fast rotation. Pulsar B1937 discovery posed a challenge to accepted theories of neutron star evolution and created new opportunities for studying the final stages of stellar evolution. It's a great tool for testing interstellar medium and gravity theories because of its steady pulse period and rapid rotation rate. Its ability to measure pulse arrival times precisely has also made it useful in the search for gravitational waves using pulsar timing arrays. The Pulsar J1614 pulsar. Another interesting pulsar is Pulsar J1614, which is situated in the Scorpius constellation some 3,000 light-years away. This binary pulsar has an especially intriguing characteristic. It is a double neutron star system because its companion is a neutron star. The pulsar is known for its extraordinarily high mass, roughly 1.97 times that of the Sun, and its 3.15 millisecond rotation period. Pulsar J1614 high mass has shed important light on the properties of matter at nuclear densities. It has put into question some neutron star composition models that indicate a lower maximum mass than what is actually observed. Moreover, the orbit of the system offers a great platform for testing general relativity theories. The orbit's exact measurements have provided highly accurate confirmation of Einstein's theory's predictions. Our knowledge of the characteristics of matter in extreme environments and the ultimate fate of massive stars is affected by the study of this system. These pulsars and neutron stars each represent the unique and fascinating characteristics of these celestial bodies. Astronomers learn vital information about the physics of harsh environments, the development of stars, and the basic properties of matter and gravity via their study. Consistencies throughout the universe. Among the universe's most visually striking objects are spiral galaxies. These galaxies, which account for roughly 60% of all galaxies in the nearby universe, have flat, disc-like structures with spiraling arms extending outward. Our own Milky Way galaxy is the most well-known illustration. Because they contain young, hot stars, the spiral arms of these galaxies are brighter than the rest of the galaxy and are locations of active star formation. Density waves are assumed to be the cause of these arms because they propagate throughout the galaxy, compressing gas and dust and causing star formation. Although the exact mechanism underlying these waves is still unknown, it's thought that they have something to do with the galaxy's central bar's gravitational pull or irregularities in the galactic disk. Spiral structures are also present in some nebulae, more precisely in star accretion disks and supernova remnants. The Cat's Eye Nebula, for instance, has intricate spiral and concentric ring patterns. These structures are created in the later stages of a star's life by the interaction of stellar winds and material expulsion. Though on a much smaller scale, the symmetry and patterns found in these nebulae frequently resemble the spiral structure found in galaxies. Despite their wildly disparate scales, these spiral patterns are similar, which implies that there are universal physical processes at work. These structures' formation is closely related to both gravitational dynamics and matter's interaction with various environments. Relationships between evolution and star formation in nebulae and galaxy development. Within nebulae, which are enormous clouds of gas and dust, star formation takes place. This is a fundamental process in the universe. For example, the Orion Nebula is a region of intense star formation, where gas and dust clouds are collapsing to give birth to new stars. Part of the nebula collapses due to gravity at the start of the process. Heat from the condensing material eventually causes nuclear fusion to ignite in the new star's core. Understanding the life cycle of stars and the evolution of galaxies depends on these areas of star formation. the lifespan and ultimate fate of the stars created in these nebulae, whether they collapse into a white dwarf, burst into a supernova, or form a neutron star or black hole, are determined by their mass. Star formation is intimately linked to the evolution of galaxies. The appearance and evolution of a galaxy are determined by the rate and distribution of star formation within it. For instance, spiral galaxies that are actively forming stars contrast with elliptical galaxies, which have younger star populations and less noticeable star formation activity. Through a variety of processes such as star formation, mergers with other galaxies, and interactions with their surroundings, galaxies undergo evolution. The building blocks of new stars are gas and dust in galaxies. As these resources are depleted or ejected from the galaxy, star formation slows down and the structure and colour of the galaxy change. Over the years, the study of these cosmic structures and processes has been spearheaded by a number of astronomers and astrophysicists. Edwin Hubble's classification system for galaxies established the groundwork for comprehending the variety of galaxy forms. Our knowledge of these structures has expanded as a result of later research by astronomers employing ground-based observatories and telescopes like the Hubble Space Telescope. Astronomers such as William Herschel and his sister Caroline Herschel made pioneering observations of star clusters and nebulae in the field of star formation, which helped pave the way for more in-depth research on star-forming regions in the future. With the use of contemporary radio and infrared telescopes, we have been able to look into these hazy, dusty areas and see the star birth processes in astonishing detail. These structures and processes have an astounding scale. While nebulae are smaller, they can still cover several light-years. Spiral galaxies, like the Milky Way, can span over 100,000 light-years across. Over millions to billions of years, the processes of star formation and galactic evolution take place, demonstrating the universe's dynamic and ever-changing nature. The universal principles governing the cosmos are emphasized by the evolutionary connections and structural similarities among various cosmic entities. These processes show a cosmic synergy, from the formation of stars in nebula to the evolution of galaxies, and from the vast spiral arms of galaxies to the complex patterns in nebula. Comprehending these similarities emphasizes the interdependence of all cosmic phenomena and offers insights into the nature of our universe. We are able to observe more and comprehend more theoretically, which helps us to gradually solve the universe's mysteries and uncover the fundamental harmony of the cosmos. Gravity as cosmic glue in galactic clusters. Galactic clusters are some of the biggest structures in the universe, made up of hundreds or thousands of galaxies held together by gravity. Gravity causes galaxies to gravitationally assemble into massive conglomerations that can span millions of light-years, which is how these clusters form. A major feature of galactic clusters is their gravitational pull, which controls how member galaxies move and interact with one another. For example, the Coma cluster is a massive cluster with over 1,000 identified galaxies, situated approximately 320 million light-years away. Such clusters may undergo galaxy mergers, galaxy shape distortions, or even the creation of substructures within the clusters as a result of gravitational interactions. Another important object in the study of dark matter is the galaxy cluster. The gravitational effects observed in these clusters cannot be explained by the visible matter, dust, gas, and stars. This disparity points to the existence of dark matter, an invisible material that accounts for a sizable portion of the mass of the cluster. The direct result of gravity's influence is observed in galactic clusters as gravitational lensing. This phenomenon happens when light from objects behind the cluster is bent by its strong gravitational field, enhancing and warping the image of those far-off objects. The distribution of dark matter in clusters has been better understood thanks to research on gravitational lensing. Black holes in stars. Nothing can escape from a stellar black hole, a region created when massive stars collapse due to their extreme gravity, not even light. Understanding gravitational extremes has been revolutionized by the study of these objects. A key turning point in this field was the discovery of Cygnus X1, one of the first suspected black holes. Cygnus X1, which is 6,000 light-years away, was discovered thanks to its X-ray emissions, which are the product of matter, being drawn into the black hole from a companion star. These systems offer vital insights into the behavior of matter in strong gravitational fields and the physics of accretion. Supermassive black holes are found at the centers of the majority of massive galaxies, if not all of them, including the Milky Way. With masses ranging from millions to billions of solar masses, these enormous objects are essential to the dynamics of the galaxy. Sagittarius A, the supermassive black hole at the center of the Milky Way, is roughly 4.3 million times as massive as the Sun. The existence of this black hole and our understanding of its characteristics have been greatly aided by observations of the stars that orbit it. The groundbreaking image of the black hole in the galaxy M87, taken by the Event Horizon telescope, revealed the event horizon's shadow against the glowing background of the accretion disk, providing the first direct visual evidence of a black hole. Less is known about intermediate black holes, which exist between stellar and supermassive black holes. These black holes, whose masses range from hundreds to thousands of solar masses, are essential for comprehending the evolution of galaxies and the process of black hole growth. The structure of black holes and galactic clusters is significantly impacted by gravity. Within black holes, the singularity denotes an infinite point of gravitational pull encircled by the event horizon, the edge beyond which nothing can possibly escape. Galaxies' orbits and the distribution of dark matter are impacted by the overall shape and dynamics of galactic clusters, which are determined by gravity. Although black holes cannot be seen directly, their effects can. Black hole accretion disks release powerful radiation that is frequently visible in the X-ray spectrum. Using powerful telescopes, one can observe the spectacular arcs and rings created by the gravitational lensing effects in galactic clusters. Numerous astronomers have studied gravity in these cosmic structures. Many of these phenomena were predicted by Einstein's groundbreaking general relativity theory. Stephen Hawking, Roger Penrose, and Carl Schwarzschild made substantial theoretical contributions to the understanding of black holes. Reinhard Genzel and Andrea Ghez, two observational astronomers, have made significant contributions to our understanding of the supermassive black hole at the center of our galaxy. These phenomena are astounding in their scope. Galaxies with billions of stars can be found within galactic clusters which can span millions of light-years. Even though they are compact, black holes have a gravitational pull that reaches great distances and influences the dynamics of entire galaxies. Gravity is a fundamental force that shapes the universe, as demonstrated by the mysterious nature of black holes and the cosmic ballet of galactic clusters. Its ability to bind galaxies, control the star's life cycle, and distort space-time emphasizes its ubiquity and strength. In addition to deepening our knowledge of the universe, the ongoing investigation of gravity's manifestations in these astronomical phenomena tests and improves our theories of physics and provides a window into the profound depths of the cosmos's grand design. The location of the solar system in the Milky Way. The Milky Way galaxy is a vast galaxy in which our solar system is but a tiny dot. Stars, planets, and other celestial bodies can be found in billions in the Milky Way, a barred spiral galaxy. Approximately 26,000 light-years from the galactic center, our solar system is situated in the Orion Arm, also called the Orion Spur, one of the galaxy's spiral arms. This location offers a special viewpoint for studying the rest of the galaxy and the cosmos. Research on the Milky Way's structure, which consists of a bar at its center, a central bulge, and multiple spiral arms that are hubs of active star formation, is still ongoing. The galaxy has a diameter of roughly 100,000 light-years, and it takes our solar system 250 million years to complete a galactic year, one orbit around the galactic center, the Laniakea supercluster and the Milky Way in the local group. The local group, a galaxy cluster spanning more than 10 million light-years, is made up of more than 50 galaxies, of which the Milky Way is just one, the Andromeda Galaxy, the group's largest galaxy, as well as several dwarf galaxies and smaller galaxies like the Triangulum Galaxy, are all part of the local group. The Laniakea supercluster, a massive structure with over 100,000 galaxies, is located beyond the local group. Laniakea, which stretches across 520 million light-years, was discovered in 2014 via observations of galaxy motions. It takes its name from the Hawaiian word meaning immense heaven and offers a more comprehensive framework for comprehending the Milky Way's role in the cosmos. Our understanding of the cosmos is constantly growing thanks to technological breakthroughs and the persistent curiosity of humans. The launch of the James Webb Space Telescope, JWST, in December 2021 marked a significant advancement. JWST is intended to observe the universe in the infrared spectrum, making it the largest and most powerful space telescope ever constructed. This will enable it to look farther back in time than ever before and witness the formation of the first galaxies and stars. Upcoming projects like the ongoing Transiting Exoplanet Survey Satellite, TESS, and the planned large UV optical IR surveyor, LUVOIR, seek to deepen our knowledge of exoplanets, galaxy formation, and the fundamental principles governing the cosmos. These missions hold the potential to open up new areas of research in conjunction with developments in ground-based observatories. Even with our expanding knowledge, there are still many mysteries in the universe. The two most profound are dark energy and dark matter. Dark matter is only known by its gravitational effects. It does not emit, absorb, or reflect light. It is estimated to make up roughly 27% of the mass energy content of the universe. One of the most important unsolved mysteries in astrophysics is the nature of dark matter. The mystery of dark energy is even greater. It is believed to be the cause of the observed acceleration of the universe's expansion, accounting for roughly 68% of the universe. Comprehending dark energy is essential to understanding the universe's ultimate destiny, and there are still unanswered questions concerning the universe's destiny. Will it keep growing forever, or will there finally be a big crunch that causes it to collapse? Alternatively, there could be a big freeze in which the universe becomes cold, dark, and lifeless as a result of star exhaustion. These are fundamental questions in cosmology, and their answers have a direct bearing on how we perceive dark matter and dark energy. From the orbit of our solar system within the Milky Way to the enormous scope of the Laniakea supercluster, our place in the universe serves as a sobering reminder of its vastness. The JWST mission and other upcoming space exploration projects represent the future of space exploration, which is poised to expand our knowledge of this vast universe. In the meantime, the riddles surrounding dark energy, dark matter, and the universe's destiny serve as guiding lights for future research and present us with a constant challenge to push the limits of our comprehension. The universe is an endless void that awaits human exploration. It is not just the frontier of space, but also of human imagination and curiosity.